All right, started the recording as well.
Perfect. Cool. So hi, everyone. Really excited to be here with you. This talk is sort of the airplane view.
No, Ethan. I'll have one flat out as well. Can move.
I'm just going to mute you here and Kira. So this is the airplane view of the LLMs that have come, in the last 2 years. From ChatGPT all the way to Llama and friends. We're going to see a couple of them, and the purpose of the talk is really to give you a framework to think about all these models that are sort of popping up every day or week, and so that you can sort of place them where they are and how they differ from one another. Before we start, it's worth saying a little bit about me. So I studied computing at Imperial College, finished around 2012. This is an interesting point in AI because this is just about when neural networks were becoming a thing. So it was interesting because when I studied, neural networks were exactly the thing to not use when you're doing machine learning. And just about when I started working, it was the only thing to use when you're doing, AI and machine learning. So I've worked as a data scientist in a couple of startups in London, companies like Seeders and Conversocial, relatively small, you might not know them. Then I went and led the data science team at the Wellcome Trust, which is a big biomedical foundation, again in London. And then I co-founded MantisNLP. So Mantis is a Gen AI consultancy. We build custom AI solutions for clients. We offer advice for things AI related when we're not building things for them. We tend to differentiate the streams of work we do into two, one being chatbot related. So things like custom RAG applications for clients, for their own data, things like customer support, for example, or other things, or document AI, for example, processing large volumes of documents, as an example, invoices, using extractive AI, the more traditional methods, but also Gen AI lately on that stream. We use the common tools you would expect, transformers, Spacey, Haystack, LangChain, DVC, Git, and others. This is just a sample. And I think in order to dive into the LLM world, I think it's worth phrasing the conversation along the steps, framing it a little bit along the steps that it takes to train an LLM. So these are starting from pre-training. This is where most of the time and compute goes. This is where we're trying to predict the next token essentially, and we're throwing web-sized data or more into that process. So it tends to sort of cost in the millions, and it takes time in the months. So basically this is where most of the time and money goes, and this is where some companies decide to keep their models proprietary for that reasons, and others choose to make them open source. And following that step, there are a couple of other steps that are orders of magnitude smaller in sort of the amount of data and compute they require. So this is things that, cost in the low thousands to train, and then in the low days as well. So this is something you can actually do, and a lot of people are doing. And a lot of the models that have been published are variations on the follow-up steps. So there are steps like instruction fine-tuning, where we're trying to teach the model to follow particular instructions that we want, something like write an essay or an email. Preference learning, where we're trying to say some sort of answers are more relevant than other answers. Both instruction fine-tuning and preference learning are sort of usually grouped together in a so-called alignment. This is where we're basically trying to align the LLM to behave the way we want. It's worth saying that most of the knowledge an LLM acquires comes from the pre-trained stage, and when alignment comes is where we're just trying steer it towards the direction that we want. How do we want to use it? There are two additional steps that are less standard that we're seeing more and more lately. One is extending the context window. So a good example would be Gemini. When it was released, it was of a particular context window, and then next version, few weeks after, extending that context window all the way to 1 million or even 10 million tokens. So this would be a step that happens after, and other optimizations in the data, optimizations in how fast a model can train. This is where the GPT Turbo lineup comes in, or faster versions, cheaper versions. This would be like an optimization step that comes after. Now, with all those things being said, it's worth saying that a lot of the difference we're going to see speak more to the pre-trained stage, but we're going to see some things that are different in the other stages as well, excluding the context window one. So we're going to see some things that are different in instruction, fine-tuning, preference learning, and optimization. But we're not going to cover extended context window, and most of the things we are going to cover basically speak to the pre-trained step. So when we're talking about differences in the LLM world, I think it's worth thinking about 4 things. This is not an extensive list, but it's a grouping that helps me think all those different LLMs we're going to try to understand and where they fit. And these 4 things are the size of the model, how big it is, the number of tokens it was trained on, how much data it was used when training it, whether that model was distilled, whether there was a teacher model that taught the student model, the model we're seeing, and whether there is some sort of optimization happening at some point that makes that model different. So what we're going to do now is we're going to go which one of them, and we're going to discuss them and speak about some LLMs that have appeared in some sort of chronological order, but not always. There's a little bit of a delay whenever I press to continue until it does continue. I'm not sure why. Okay, got it. Cool. So first thing to talk about is size, right? How big is the model? So when we're talking about size, I think it's worth stepping back a little bit and speaking about the scaling law that exists in LLMs. So this is a law that was proposed around 2020 from OpenAI. It's a very simple scaling law. It predicts the loss a model will have given its model size and the data number of tokens it is trained on, with some constants A and B and E, which gives us the ability to sort of predict not necessarily the performance, but performance with loss correlates. So it gives us some sort of intuition of how much or whether one model will be better than the other. So from the scaling law, it's worth seeing that there are basically 2 main parameters that make LLMs different one another, one better than the other. And this is 1, model size. The bigger the model, the smaller the loss. 2, number of training data. The more data you're throwing into the model, the lower the loss again. And what is the importance of this, how big a model is and how much data we're throwing? Depends on the parameters on those constants. So it's worth saying that until 2021, the scaling law appeared around 2020. The common wisdom that you probably have seen is, let's scale the model up. Let's make the model the bigger it is. And there is truth to it, as we saw from the scaling law. The bigger a model is, the better we are expecting it to be. That was definitely true. Interestingly, to this sort of scaling the models into a larger and larger domains, just to understand the limits of this, Google trained a model around 2021 called Switch Transformer, which was basically a very similar model to GPT-4. In all intents and purposes, you might actually think this is a GPT-4 model because it's a mixture of experts model, it's around the same size. And the basic reason that is not GPT-4 in some sort of ironic way to Google is because it was trained on orders of magnitude less data than GPT-4. In fact, it was trained on the same amount of data from memory that GPT-3 was trained on, around 300 billion tokens, which is nothing, as we will see later on, for that size. So it was a little bit of an unsurprising model. Of course, it gave them insights into the mixture of experts and how that scales. But just to say the irony of things, that we could have arrived at the GPT-4 moment a little bit earlier. Now, just to understand the effect those parameters are having before basically the ChatGPT era, but just to speak to the effect that model size has, it's worth putting some numbers into that scaling law and just seeing some of those differences, just to understand what happened before and what's going to happen after. So if we start by looking at, for example, GPT-3 and Palm models that were sort of like in the pre-ChatGPT era, you will notice that the model loss at that point in time, where they were basically scaling the models up but not scaling the data up so much, the model loss is not so different. The loss is quite close to one another. And the main reason actually Palm was a better model than GPT-3, if anything, was because it was trained on more data. So if you see next to the model loss, the data loss, you will see that the reduction there, it's much more significant than the model loss. Meaning that at that point in time, as we will see later on.
What is data loss?
Let's answer questions in the end, if possible, just because we have a lot to cover, but let's keep that question. In short, we're talking about the scaling loss still. So basically the equation we show here, the loss that comes from the first term, the loss that comes from the second term. And all I'm saying is, back to that slide, that the loss from the size of the model being bigger in the Palm case was actually quite small, and the main reduction or increase in performance came from throwing it more data points, essentially. This came to a new scaling law, basically when Chinchilla was a paper from DeepMind was released, that basically introduced a new law, changed slightly the parameters until that point, and demonstrated how all the models until that point were a little bit undertrained. And we can see that if we go into the Gopher and Chinchilla, and then we see what is the two models that actually behave relatively similar. As you can see in the final loss on the right, the losses we get are very similar, but actually Chinchilla is actually 3 times smaller or more, but it's just trained on more data. And that by itself, if you check the data loss, is what makes it possible to perform on the same level as a much bigger model, which was Gopher. Anyway, all of those things are to say that before ChatGPT launch, there was this sort of, let's make the models bigger trend that got all the way up to a point where models were a little bit undertrained. They were quite large with not a lot of data. Of course, having a larger model is important, as we saw from the scaling law, but it got to a point where it wasn't as important. And to illustrate that, this was the graph from the Chinchilla paper. So the dotted line was the scaling law that was followed before. The model were trying to scale under this sort of false scaling law that existed initially from the 2020s. And the line that sort of follows the dots is the correction, the sort of the Chinchilla law, and all models that followed after that basically pretty much follow that line. Okay, and we're going to see those models now. These are all to sort of, first of all, introduce that model size is important, and it's still important to this day. There are some diminishing returns after a point, and we've reached those diminishing returns before the ChatGPT era, as we saw just now. And there is a model data size trade-off, which was off before Chinchilla and then was corrected with the new scaling law. And basically, after Chinchilla, what happened was, we're going to see it in 2 slides, but this is a good segue basically to speak on the importance of the data, how many data and tokens we throw into the training process. So basically now, back into the scaling law, we're going to switch a little bit our attention into the tokens, into the second part of this equation, right? And I'm saying all of these things just to say what happened after Chinchilla, ChatGPT launched. Like incidentally, Chinchilla was sort of like the new sort of correction to the law, but then we had the ChatGPT era, and then we had all these sort of LLMs we're going to start seeing that started following this new updated scaling law. So they weren't, sort of reaching into new heights in terms of model size, 2 trillions, 10 trillions, but they were reaching into new heights in terms of how much data we were throwing them. And this is a good illustration of that point, right? The main models that have been published that are pre-trained from scratch, essentially, are things like, the Llama series, and these are a little bit in chronological order. So Llama 1, Falcon, MPT, the Llama 2, all the way to now Mistral and Llama. I'm keeping the parameter size here constant just to make the point of the difference the number of data we're throwing into those models make into their final performance. So as you can see straight away from this, you will see that we're increasingly throwing more and more data into those models, starting from Llama 1, which was the 1 trillion tokens, and then going all the way to the Llama and Mistral, which are in the 6-8 trillion models, and DBRX actually is trained on 12 trillion tokens, which we're not going to cover though. But anyway, the model loss remains the same because all of the models we're comparing here in this slide are on the same size. But as you can see, of course, more data thrown in, lower loss, means lower loss in the end, means a better model. A lot of the time when you're actually assessing an LLM nowadays, the first interrogation point you should sort of be making is how many tokens it was trained on. DBRX, which we're not going to cover, it's a good example. It's trained on 12 trillion tokens. That alone makes it a very capable model, but then you have to look at all these other things as well. Of course, if you are careful and you remember the Chinchilla law, which was basically the new scaling law that I told you new models follow, and they do follow it to some extent. Had it that Chinchilla was a 70 billion parameter model, and it was trained on a little bit more than 1 trillion token. So if you're paying very close attention to either the presentation or what's happening with LLMs, you might be wondering, why does Llama 1 or any of those models basically train on so much data? Shouldn't they be orders of magnitude bigger to follow the Chinchilla law? And the reality is they're not following the Chinchilla law. So let's see what's happening. There is a trade-off to be made with the number of tokens you throw into a model, which is the question of, instead of under-training, over-training it. Basically, if you try to solve the equation, take the scaling law and say, how small can we make a model? And how much data we need to throw into it to get the same loss. So basically, if we had Chinchilla as an example of a 70 billion parameter model with 1.4 trillion tokens, how small can we make it? Can we make it 7 billion? And if we make it a 7 billion, how many tokens do we need to throw to get the same performance? This is important because as we make models small, of course, they're more inference optimal. Like it's faster to run, more friendly and costly for when we're using them, not training them. So as it was pointed out in this blog post, which I link here and have to pass generally all the slides with links after, there is a way to solve this equation and say, okay, we want the same loss, but we want to shorten the model with the parameter Kn, increase the tokens with the parameter Kd, and then for the amount of Kn we want to short, we can get how many tokens we need. Long story short, this will require more training, so there is a little bit of overhead. We're spending not a compute optimal budget, we're training more, but we're doing that because we're going to be doing a lot of inferences and it's more inference optimal. So come inference time, it's going to be cheaper for us, essentially, is the idea. And what's interesting here is that this solution of the compute overhead, essentially, that we need to incur to train those models follows this nice line. This line, by the way, appeared in the first scaling law as well. So it wasn't completely something that this blog I'm linking introduced, but this blog I'm linking did make it a little bit, draw a little bit more attention to it. And basically the graph we're seeing here sort of says, okay, if Chinchilla is sort of the compute optimal size, number one, like the fraction of the optimal size, all the models that came after it are basically smaller than the compute optimal because they're trying to move into more inference optimal sizes. But as you can see, the amount of compute and data, and also intuitively you can think about it, that you need to throw into those models to achieve the same performance grows exponentially. So you might argue there is a point that you want to stop doing that, because you're basically going to get to a point where you have to throw thousands of trillions of, you don't want to spend all this compute and all these tokens just to make a 1 billion model perform like a 1 trillion model. And this is a little bit of a subjective point, but in the blog post, then it kind of makes sense. Like you might say this is the critical model size point illustrated here, where the overhead is 100%. You're basically spending twice the compute. You're just about where it's going to explode and you're going to get diminished in return. This is the point you stop. And what's interesting with that point is we can actually get a feel of the model sizes and the number of tokens by plugging in the numbers that we expect. So in the 3 billion range, this would be something like 3 trillion tokens. In the 6 billion range, it would be something like 6 trillion tokens. And these are exactly the numbers that Llama, by the way, used. So they released a model in the 2 billion with 2 trillion tokens, 6 billion, 6 billion. Mistral is around that sort of sweet spot. But it's worth saying that in the bigger models, like 20 billion and the 40 billion, we still don't have, but expect to have, models that are inference optimal. So there's still a lot of room to grow into that sort of nice range of, from 12 billion all the way to 70, which we've seen many models. We haven't seen all the way up to the 70 billion for a lot of those sizes, the inference optimal models for those. So again, as a recap, we said that more tokens means, better model, as sort of the scaling law dictates anyway. It also has diminishing returns. There is a point that we saw in the graph where you have to throw a lot of exponentially more data. So this also has diminishing returns, which we've sort of reaching at now. There is a subjective inference optimal size. I'm not going to say that we might not see a 7B model that is trained on 12 trillion tokens. Someone might do that. And, like this would be moving that subjective inference optimal model a little bit further. And there's a lot of room for inference optimal models in the 12 billion, 70 billion range. This is just something that you're probably going to see in the coming, days and weeks and months coming out. Okay, so these are the main two components that we saw in the scaling law. The model size essentially, and the number of tokens a model was trained on. We're now moving into distillation. So distillation is the idea, as you probably know, that you're going to start from a teacher model, something like a frontier model, depending on the time that these things happened, like a GPT-3, 4, whatever the best model was. In a lot of those cases, this is GPT-4. And then you're trying to make a smaller model behave as close as possible to the teacher model somehow. You're trying to connect the two and say, okay, we want some sort of distillation of that knowledge. We want to get the student model to go as close as possible. In a lot of those cases, Llama is being used. It was one of the first, and then basically it kept being one of the best models. Of course, nowadays we have alternatives like Mistral, but in a lot of the sort of the models we're going to see now, the combination was some sort of GPT-4 Llama combination. And it's worth saying, why does this process make sense in the first place? Why are we not training a small model to begin with to be as capable as the big model? And we have to go through that sort of teacher-student distillation. And there's a lot of, it's an open question, but there's a lot of sort of research suggesting that this probably has to do with the fact that the teacher model provides a much richer signal into the student model, a signal that is just difficult to replicate without having the teacher model in the first place. Kind of like in a human situation where a teacher sort of teaches someone and it's just much harder to gain the knowledge in the first place. But if someone has the knowledge to pass to you, so in the case of LLMs, this is basically providing the right answers in the right format, as we're going to see in the next slide. Something that the pre-training data, which is destroying all the entire web, is not necessarily all at the best possible and highest quality state to learn from. But this is only part of the answer. And it's worth saying, of course, distillation gets you close, but of course there are limitations, which we saw from the scaling law. You can get close to the teacher model, but up to a point. And of course, is a technique that might be very applicable to some sort of industry cases a little bit more, where you're trying to distill from a larger model that is a general model. It does a lot of things, and you want to learn to do one thing. It's definitely like something you can sort of take and use there. But if we're talking about how we can sort of make like a smaller model be general enough, there are sort of cases where this process comes with limitations from that distillation, where some things are not learned because they're not part of the distillation. The model seems to behave the same as the teacher model, but because we've never sort of distilled all the general ability it has, it basically falls short in other cases that, you know, are still important to us. Anyway, this was just an intro, and it's worth saying that the distillation sort of targets nowadays a little bit more the instruction fine-tuning and preference learning part, as we're going to see in the next slides. So the simplest way to do this distillation, because nowadays it's quite simple, it used to be that you had to connect the two models and provide the loss and basically give just a richer signal, like probabilities flowing from the teacher to the model, from the teacher to the student, and this being like that rich signal. Nowadays, though, it's a much simpler process, and the simplest of those processes is to basically go to previous ChatGPT conversations, which actually are available online in a website called SearchGPT. You can take those conversations, they're already rich in signal, you know, people that are trying to use ChatGPT and have follow-ups with it. So, you know, high quality content from a high quality model. You can take those conversations and train on them. And it's exactly what Vicuna did, and got to very close results in a lot of sort of benchmarks to, you know, the GPT-3 and 4 lineup of models. Not exactly there, but, you know, it's as, you know, as close as you can hope to get by doing this. Of course, this was the the sort of, you know, maybe the easiest way to do it, but there is also the structured way to go about doing that. And actually a model that came before Vicuna, if you remember, was Alpaca. And this was the idea that, look, we can actually get a model to create an instruction fine-tune set. So we can get GPT-4 or GPT-3 at 0.5 or what was available at that point, create the instruction data set that we want automatically, and then use that data set to align the student model and get it to perform as good as or close to the teacher model. Of course, when we're getting the model to create this instruction set, it gives the information in this sort of rich, as we said and described, way that the teacher model knows how to do. And then come time where the student model is trying to learn it, it's much easier to jump into a bigger performance than using a different instruction set. Anyway, so you can create the instruction set automatically. This is what Alpaca did back in the days, quite cheaply. You can use like the teacher model to create that data set, fine-tune on that, and then get closer to the teacher model. As sort of the techniques progressed over time, we also saw the importance that the information, as we're describing, and I was saying again and again, this doesn't need to be, it's important that it is complex, essentially. And this is a theme that we're going to see again here in this distillation process. So a technique evolved where you start from a simple instruction and you try to use a teacher model to make the instruction and response more and more complicated to enhance the richness of the signal. The more complicated the instruction, the more complicated the solution. You can use chain of thought prompting there. You can make the responses complicated, the instructions complicated, and this is a richer signal to learn from and get even closer to the teacher model. And this is exactly what Wizarm LM did, which sort of performed even better than the other models. Of course, you might have seen, it's worth saying until this point that a lot of those models that we're talking about, and distillation comes with that cost, come under restraint licenses. Because of the fact that you do use a teacher model, it comes with limitations to what this sort of auto-generation of data and using that model to learn from you can do, right? So all of those models, Vicuna, Alpaca, Wizarm LM, come with restrained languages. Phi is another model you might have heard of. This model, unlike the other ones, was actually trained from scratch with the idea that, not very different to what we were describing before, but that textbook-like examples are the best type of examples to learn from. This is not so different to what we were discussing so far, because textbooks are that sort of rich signal you want to learn from, that we humans also learn from, right? So this is where you're it's like handing off a textbook to someone where the problem needs to be described thoroughly, nicely, and a solution exists. And this type of data set exists because we humans learn from them, but you can also auto-generate them. And they did also auto-generate those examples. So you can use a teacher model to create textbook-like examples. And those textbook-like examples tend to follow like this nice, high quality, high complexity point where you can actually learn and get very close, as we were saying, to the teacher model with a very small model. In fact, Phi goes, like if you remember, to around 3 billion and sort of performs as well as 20x, models 20x its size. Now, Phi, interestingly, because it's trained from Microsoft, and because Microsoft owns the right of GPT-3.4, is the only one of the distilled models that comes in with a commercial license. So this is something to flag that is a rarity. If you are in a case where you have the license to the teacher model, you have the ability to make that open source with the license you want. And Microsoft was the only one basically that was able and did that. There is a new technique that sort of summarizes a little bit what we said on distillation, which doesn't speak to a model, but it speaks to the summary of all of the things that distillation-wise have been happening. So I just thought I would mention this is a new technique that basically auto-generates the data set that you're going to align your model on. And it does it by realizing that there are 3 important ingredients, which we discussed and I mentioned a couple of times, into creating the best possible data set to do that. 1 is the data set needs to be complex. 2, it needs to be high quality. And 3, it needs to be diverse. So to do that, the technique basically goes through a process where it involves the complexity, similar to what we saw before, but it also ranks the quality, again, using a teacher model. It keeps only the most complex, high quality examples, and then it goes and calculates how similar those examples are and keeps them a diverse range of those examples. And this is a technique you can use. It's an automatic technique, and it sort of can get you close to a teacher model, as we said. So again, as a recap, distilled models are trained on data that are generated from teacher model. Nowadays, there are a lot of models you've seen that sort of are distilled models, essentially, over the last 2 years. They usually come with a restrictive access, exactly because of the fact that the data they are trained on come from the teacher model, with the exception of Phi. And what we know for that part is that the data sets need to be complex, high quality, diverse. These are the important points that all those papers are trying to hit one way or the other. Which actually leads us to the last part, which is optimizations, and the shortest one. And this is just to cover a little bit of some other models that have been happening and some other things that make models different. Maybe you've seen a model from Hugging Face called Zephyr or a model from Argila called Notus. These are sort of gained some traction where they were trained. It's worth saying what is the difference in those models. And both of those models were basically aligned versions of really strong open source models to begin with, models like Llama 2, Mistral, Llama. And what's different with those models is basically the data sets for instruction, fine-tuning, and preference learning, both of which there are open source large data sets people use nowadays, like UltraChat and UltraFeedback. In the case of Zephyr, they targeted UltraChat, and they found and they created a subset of that data set that was more diverse, and that on its own was enough to boost the performance of the model. Just having a more diverse data set than using a less diverse one. In the case of Notus, they targeted ultra feedback a little bit more, and they noticed that there are some examples in that data set again that were basically noise. They were sort of high-ranked examples, so high-ranked examples with negative feedback. Essentially, humans were saying something is wrong here, but the feedback that was given to the model was high. So by removing that, doing that cleaning process, removing that noise, they were able to get even better performance. It's worth saying that all those models, this is not an extensive list, they are not exactly the same, they are very similar. All these models you're seeing being announced, they follow a very similar architecture, but there are differences, which are not those super important. But just for sort of some sort of completeness, I thought I'd highlight some of those. You know, you can use a different activation function, which has been shown, like Sweet Glue, which has been shown to be slightly better and more stable. Doesn't change results necessarily so much, it makes training easier. You can use a different type of attention, like multi-query attention, grouped query attention, flash. This is where you're targeting to be a little bit more efficient. When you're decoding, you want to be faster. When you're training, you want to be memory efficient. You might use a different attention mechanism there. So it's going to make a massive difference performance-wise, but it's worth highlighting that it is a difference. And last point is, noticed like a sort of an approach from China, basically called mini CPM, which is sort of like worth highlighting, which is there was some optimization that was done in all of those hyperparameters, as we know that all these models are trained on, and they're pretty standard nowadays. But they went on and did hard work, so to say, and basically challenged those parameters. You know, the weight scaling, you know, when we're doing layer norm, in the transformer block, the learning rate, batch size, the scheduler, just did a deep exploration of what are the best of those parameters. And they managed to train a 2 billion version model that was as good as a Mistral 7B, which I only say just to point out that there is a little bit of more performance to squeeze come optimization time for when we're training those models or how we're training them. So some of the things that might be different in some models, but I would say the least important is that last bit, which is the optimization. Cool. So this was the last slide, and hope we have enough time for questions.
Thank you very much, Nick. Let's see, I think we have some comments or questions in the chat.
And have a look.
So there is a question. So please raise your hands if you want to ask a question so that we try to keep it a bit organized, but feel free to add them in the chat. Ibrahim,
someone asked actually during the,
Yes.
someone asked, yeah, I'm seeing Ibrahim's sort of question about data loss and the model loss.
Go for it.
Maybe it's worth, I think we sort of answered it briefly, but you know, in case it was unclear, it was basically referring to these two parts in the scaling law. The model loss being the loss that comes from how big a model is, and the data loss being, you know, the loss that comes from how many data points it is trained on.
There is another comment by Serge about bfloat integer 8 not being mentioned. Don't know if it's clear or Serge can provide more info on that. Serge, feel free to open the mic.
Yeah, I think it sounds like, from what I'm reading, happy to be proven wrong, that we're talking about some sort of quantization, you know, that fits nicely into the optimization, and, you know, we left out, you know, optimization, quantizing those models, adapting those models using, you know, techniques like LoRa and QLoRa. Yeah, I mean, 100%. These were not mentioned.
Nick, I have a question on the equation you have in front of you. I don't know if you mentioned it. Maybe you didn't. I missed it. What is the intuition about the last term, so which is irreducible? How did that end up in the equation? So what
So it turns.
Yeah.
It turns out that there's only so much you can predict. There is a point where you have to guess, right? Like, I mean, you know, a particular sentence can be completed in 2 different ways, and that's fine. You know, like you cannot get 100% accurate in predicting the next token. There is a term which makes sense from language that you cannot reduce. This is something you cannot basically predict. And I think this is a term they also estimated. I'm not 100% sure if it came from information theory or they estimated, but it speaks to the fact that you can only get to a point, and after that, it's probabilities.
And maybe a follow-up, are there other kind of efforts to, I mean, for the scaling law, I mean, are there continuous kind of efforts to update the parameters or find better estimates on this law?
Yeah, I think this is an interesting one, because of course we're not part of those labs that are doing that, but you know, from what is being shared, it seems like all these laws are sort of always flawed in ways, and you know, like that's why this sort of slows down a little bit the progress, in that every time a new frontier model is being trained, a new scaling law seems to be fitted and adjusted. So as we're sort of pushing the boundary, we're always readjusting that law a little bit, is what is being discussed, but not as open research. We don't have like a paper saying, you know, now that we are in the 1 trillion range with GPT-4, what have you, this is the new scaling law. The last we know of scaling laws was Chinchilla, and everything else, scaling law-wise, seemed to be private to my awareness.
Thanks. There is another question by Serge. So what are the other big things are worth to check that were presented in the last year?
Yeah, I mean, difficult to say. I mean, there were so many things. So as I think you said as well, we didn't cover a lot of the space where how is it that it's easy to sort of use and fine-tune a model, the sort of the quantizing it and adapters, and you know, like just making it easy to fit into, you know, like smaller. I mean, this is an important part. We didn't cover a mixture of experts. We briefly sort of, and it's an important point because of it offers like an inference-friendly way to scale. It's not necessarily that those models that are sort of bigger and they are a mixture of experts are less capable. They can be thought of as the same size as what is, you know, like the total size of the DBRX, for example, model, or the GPT-4 model. They can be thought of as being at that size, but it's just sort of like an optimization in the sense, okay, comes inference time, you use less parameters, so it's more friendly. What other things we might have missed? Yeah, I mean, there's a little bit of a discussion to be had on the amount of data, which is sort of related to all this conversation. How much data is available? Are we running out of data? Like if you follow the numbers closely, I spoke about, okay, maybe we're going to see like a 60 billion model with 60 trillion tokens, but like, you know, like, are there 60 trillion tokens? There are papers that speak to, you know, maybe they're all the way to 100 trillion tokens that are high quality, and, you know, like there's a little bit of that. Of course, we didn't cover anything that is multimodal. All these models are now not only text, things like that.
There's another
I'm reading these other questions. Yeah, it says, what's the decisive point where RAG is not sufficient anymore and you'd go with fine-tuning an open source model? I think this requires a little bit of an interpretation, and I'm going to make that interpretation to be, there's a point of, you know, like you have some sort of information, be it the web or your client's data, and RAG, of course, sort of grounds it and, you know, gives answer to that sort of corpus nicely. And there is a limit to that. for a lot of reasons. Because, like, it's not trained to answer those type of questions. It's not trained to answer, as we saw in a later paper, to answer with context that is relevant. And this is where you start by sort of doing RAG and prompts optimization, and you end up doing fine tuning just to get these last bits, learn the domain better, the type of questions that are being asked, learn to deal with the kind of things that are being retrieved, if this is what the question meant.
I think we got a thumbs up, so I think your assumption and interpretation was fine, Nick. Are there any more questions? All right, so I guess that would be it. If you want to connect with Nick, you can find him on LinkedIn. So MantisNLP provides some very, very nice tips and very nice posts on LinkedIn about all things LLMs and generative AI. So have a look. And again, thank you very much, Nick. And it was really nice. And thank you everybody for being here. See you in the next one.
Thank you.
Bye-bye.